Good morning, everyone. It's a pleasure to be here. So my name is Bongsu Kim. I'm the CEO and co-founder of Roboligent. Today, I want to talk about what I believe is a missing piece in the current landscape of physical AI. We are seeing incredible leaps in the robotics and AI, yet industrial automation still faces a massive gap between demos and reality. So I want to argue that two critical components, software robot actuation and force-aware policy, can play a decisive role in closing that gap. Today, we see a lot of impressive videos, but most are still in pilot phases. There are a few cases out there, but even those aren't true commercial deployments yet. Yes, of course, today's robots and physical AI still fall short on speed, dexterity, and cost. We know that. But here's what's interesting. When we actually talk to industrial customers, they're more realistic than you expected. So they're willing to start with the simple, less time-sensitive tasks, but hard requirement, though, is like a reliability and safety. Those are non-negotiable. One of the main technical difficulties in achieving reliability and safety is that most industrial robots are inherently averse to physical contact. Collision avoidance and safety stop lower the safety concerns, but cannot help the contact with the situation that much. Robots need to be compliant, stable, and safe during intentional physical contact and still apply force precisely as intended. But usually, existing compliant robots come at a cost, imprecise motions and low payload, which is not practical for industrial use. There's another challenge in learning side. Robot policies like VLAs learn mostly from the visual input. And the action data they train on, position, speed, and angles, those are all kinematic information conditioned on RGB images. They don't capture how hard the robot is pushing against the surface or machine. So it's like learning to play tennis just by watching YouTube. You can see the motion, but you have no feel for the ball. You're never gonna be Rafael Nadal that way, right? So. And even if the robot works perfectly, you still cannot deploy commercially until you meet industrial standard. Biped humanoid robots cannot yet meet the cooperative safety criteria where robots get separate from human with marked joint. The risk of falling itself disqualifies them. But in reality, most industrial customers don't want to redesign their floor layout. They just want to place a robot right next to a human and get started. For that, robots need to meet collaborative safety criteria where working side by side with humans is safe by design. So what's the solution? We need two things. A robot body that's safe to physically interact with, and a robot brain that actually understands physical interaction. On the body side, soft, precise, heavy-duty force control actuation. So the robot can make a stable, safe contact and apply force exactly as intended. On the brain side, the VLA model needs to learn not just what things look like, but how they feel. Force, resistance, haptics, all of it. These two have to work together. At Roboligent, we built two things from the ground up, a proprietary soft actuation platform and force-aware VLA. Together, they power our robot, Robin. Robin doesn't just move a target position, it feels and it reacts. That's what allows it to handle tasks that were previously too risky or too unreliable for robots to do. This is how we bring robot behaviors closer to how a human actually works. A natively software arm acts as a physical safety buffer. When something unexpected happens, and in the real world it always does, the arm observes it. With a traditional rigid robot, an unexpected bump like this, it could damage something or send the tote flying out of the gripper. Soft actuation is naturally resilient to uncertainty. It reduces impact force by up to 10 times, and that's what allows our robots to meet collaborative safety standards. Now let's see soft actuation in action across different context-rich tasks. Sliding a glass plate into a tight space, inserting a charger, these tasks require the robot to allow a constrained path, follow a constrained path while keeping contact forces under control, something which robots struggle to do safely. Or assembly, pressing parts together with precise the right amount of force, or lifting a heavy box by hugging it, and where both arms need to squeeze, coordinate, and balance the load together. These are exactly the kinds of tasks where software actuation makes the difference. But a better robot body alone isn't enough to achieve industrial reliability. We also need to rethink how we develop physical AI for industry. Most big lab VLAs target general purpose autonomy, but in practice, that often means low per task success rates, which doesn't work in industrial settings. In industry, what matters is task success, deterministic behavior, and tight synchronization with the environment, including equipment, sensors, and task management system or not. So instead of chasing general autonomy, we think the better path is a small and data-efficient VLA integrated with the deterministic task planners like a finite state machine or a behavior trees. Following this design philosophy, our AI stack combines a small and high-fidelity VLA with deterministic execution logic. The VLA is small and focused, trained on specific industrial skills like gripping, picking, and screwing. Pair with the execution logic, and you get the adaptability of AI with the reliability the industry actually needs. High success rates with far less data to get there. Let me show you Robin in action. This is fulfillment center task, part of real industrial workflow replicated in our lab. What you're seeing is our small force-aware VLA running on Robin, organized by deterministic execution logic, trained on just 200 episodes, about 30 minutes of demonstration data. And notice this picking motion here is fast. It's a running inference on the local onboard machine. This is what data-efficient, industry-focused physical AI looks like in practice. Before we wrap up, let me give you a quick look under the hood of our force-aware VLA. We use a small VLM with a DIT action block, taking image, language, and proprioception, including force data. The core innovation is our haptic flow matching loss term. We train a haptic field that captures expected force trajectory during successful task execution. At inference time, deviation from this field triggers real-time motion correction. As a result, this force adaptive policy can reduce interaction force by 70% compared to a standard flow matching model. This means the robot is doing the same work with a much softer and safer manner, reducing failure rates. This work is led by Bongsu Kim, a Ph.D. student in Dr. Peter Stone's lab at UT Austin. So let me wrap up. Today's physical AI robots have vision, language, and action, but force and tactile feedback, the missing modality is what context-rich tasks actually need. Industry isn't just necessarily asking for general autonomy. They want guaranteed, reliable, and safe automation. Reliability above 99%, safety compliance, and deployment that fits into existing workflows without disruption. That's what we are building at Roboligent, a robot body that's safe by nature and a robot brain that can feel. Thank you for your listening. During the guided tour today, you are welcome to come touch Robin in person. Our team and Yunu will be there to answer any questions. Thank you.
Any questions?
So, there is all these dynamics of economies of scale, and depending on where you go, hospitals, manufacturing, homes, right, pricing changes dramatically. So, do you see a path to, go the prices that a lot of households and industrial setups demand? Or do you think there's going to be a dramatic sort of difference in pricing depending on the region? And then if we go really very low cost in robotics, the margins are going to be very slim, and we know that sometimes we don't like it in the U.S. Well, we don't like it, right? Point.
Yeah.
So do you think that that we're going to have kind of a race to the bottom, and somehow that's going to have a correction because of the large quantities of robots that we're going to be selling?
So you're asking how is the cost structure these days is play a role in different regions of the industry, and then how we can anticipate wider dissemination, overcoming the cost kind of challenges. I think that's what robotics company these days is really try to solve. First approach is by doing a mass production approach. So it's a sum of a couple of big companies is doing thousands of production. Still, that production cost is still over, I would say $100,000, $200,000, something like that. So, and another approach is that, so you talked about a thin margin layer. That is most the case of a Chinese manufacturer there, and then because they are selling most of this hardware, and then sometimes they lose money out of selling those. So I think it's the best way for United States player. I think is we are more focused on adding values on top of hardware. So, and then we can allure customers to use it a daily basis, monthly basis, and produce more a productive than they pay. I don't know, just low kind of a end of I don't know, just salary kind of level, monthly cost, things like that. So in our case, for example, our robot has around, this is a secret, but it's around, the building cost is around $60,000, $70,000, something like that. So, and then with margin there, and then we can sell it $3,000 per month, something like that. I think when we talk to industrial customer at least, that is kind of really welcomed from customers, even though it is not give huge margin to us, but still it's doable. So I think that's kind of stretching somehow is collaborating with a funding side, and then with the robot side is absorbing some upfront cost, and then maybe deploy over the time. That is more some realistic approach, I think.
Thank you so much. Let's give Dr. Kim another round of applause.
Thank you.